So in this video, we're going to find a limit by rationalizing a numerator. So it's frequently the case when we're finding a limit that a useful technique is to either rationalize a numerator or a denominator. So in other words, when we have radicals, we want to eliminate the radicals from either the numerator or the denominator. And the tool that we are going to use is going to be multiplication by a conjugate. And so what we want to remember is that if we have, just a quick review, if we have two terms a and b separated by either a plus or a minus, the conjugate will be the same a and b, but separated by the opposite operator. So if this is plus, I'll put a minus. If this is minus, I would put a plus. And the idea is when we multiply these two terms, we're going to get a times a is a squared, a times minus b is minus ab, plus b times a is going to be plus ab, and then we get plus minus is minus b times b is b squared. And the key is that the middle terms cancel. We get minus ab plus ab is 0. We wind up getting just a squared minus b squared. So the shortcut is when we're multiplying two terms that are conjugates of each other, the same two terms, one separated by plus, one separated by minus, the shortcut is we can just multiply a times a, and then we'll get minus b times b. We get a squared minus b squared. So in this case, I'm going to rewrite the original problem, which is the limit as x goes to 0 of, and the fraction bar there means I really don't need the parentheses. So I'm going to go x plus a minus the square root of a over x. And the first thing we want to look at is the denominator, which is x. And we want to immediately look at the limit we're taking. We're taking the limit as x goes to 0. And we want to think about what happens when we plug 0 into the denominator. And we immediately see we'll get a division by 0, which tells us that to find this limit, we cannot plug x equals 0 in, because we'll wind up with something that's undefined. So I can't plug x equals 0 into this expression because it would cause a division by 0. But what we can do is multiply the numerator by its conjugate. So I'm going to rewrite here. I'm going to take the limit as x goes to 0, and I'm going to take x plus a minus the square root of a, and this is over x. And I'm going to multiply by the conjugate of this. I'm going to multiply by x plus a. The two terms are the square root of x plus a. That's playing the role of this. And the square root of a is playing the role of b over here. So I have the square root of a. And here they're separated by a minus. So here I'm going to separate them by the opposite operator, a plus. And the idea is I can't just arbitrarily multiply by this expression, but if I multiply by the number 1, then I get an equivalent expression. So to multiply by 1, I'm going to also multiply the denominator over here by the same thing as I'm multiplying the numerator by. So I get x plus a plus the square root of a. So this expression simplifies to 1. So I can multiply this first expression times 1 and get an equivalent expression that will just look different. So when I multiply, I get the limit as x goes to 0 of, and I can do the shortcut. A times a is a squared. So it's going to be square root of x plus a times the square root of x plus a is just going to be the square root of x plus a squared. And then I'm going to get minus the second term squared. I get square root of a times square root of a is the square root of a squared using the shortcut over, and here I'm going to get x times the square root of x plus a plus the square root of a. And I don't want to distribute this x, and I'm going to leave it in a factored form here. And then I want to recognize in the numerator that the squaring is going to cancel the square root, which is going to leave me with x plus a minus the squaring is going to cancel the square root. So the square root of a squared is just going to be a over, again, don't distribute the x into the numerator, x times the square root of x plus a plus the square root of a. And then a minus a will be 0, so this is going to leave me with the limit as x goes to 0 of x plus 0 is just x over x times the square root of x plus a plus the square root of a. Pull my fraction bar out. And now I see that I have x over x, and I want to recognize that x divided by x equals 1 as long as x isn't 0. And x isn't going to equal 0. We're taking the limit as x gets as close to 0 as we want without ever letting x equal 0. So I'm going to pull my work over here. I get 1 in the numerator, so I have the limit as x goes to 0 of 1 in the numerator over the square root of x plus a plus the square root of a. And what I want to notice now is that if I plug 0 in, I will not get a division by 0. In fact, the domain for this, the only restriction I have is that x plus a, to get real numbers, I need x plus a to be greater than or equal to 0, and I need a over here to be greater than or equal to 0. I need these two things to be true. So it looks like I can go ahead and just plug my 0 in right now. I get 1 over the square root of 0 plus a plus the square root of a. I get 1. And notice I drop the limit. As soon as I plug in my real number 0, I'm going to drop the limit notation. I get 1 over 0 plus a is going to be the square root of a plus the square root of a. And this simplifies to 1 over 2 times the square root of a. And then I look at this and I say, what is the only restriction I have now? Well, I see the only restriction I have is that a needs to be greater than 0. I can't plug a equals 0 in, or I get division by 0. And I can't have a as a negative number unless I am willing to accept complex number results. So here is the final limit. Again, the tool that we used was rationalizing the numerator. We got rid of the radical sign, the square root symbol in the numerator. This doesn't always work, but this is always something that you can try when you're taking a limit involving a sum or difference of radicals.